gradients from OpenAI people. So I was given this task 2 days ago. I had read the paper beforehand though, and I read it again the last couple days. So I would appreciate if you guys can chime in and give me feedback and join the discussion. It's not a very familiar topic to me, because I don't have any hands-on experience with reinforcement learning. I have only, joined reinforcement learning paper discussion groups before. So I'm kind of familiar with the math behind it a little bit. So let's start. The paper Evolved Policy Gradients. They present a new approach to standard policy gradient method by designing another loss function that trains the policy gradients, and they go back and forth inside two loops. So here it says the idea is to evolve a differentiable loss function such that an agent which optimizes its policy to minimize this loss will achieve higher rewards. So the objective of reinforcement learning is to learn a policy function. A policy function is, giving a state in an environment. A policy function outputs what move to take, what action to take. So for a standard example of kind of like an Atari game, you have maybe only four basic functions. You just move right, left, up, or down. And giving a state, maybe there's some ghosts chasing you or something. What would the agent do to survive? And that is encoded in the reward function. So this paper, to reiterate myself, doesn't only learn a policy gradient directly, but it learns a policy gradient through another loss function, which is actually trained on evolutionary strategies. So it's quite an exotic concept. It's kind of like convoluted. And then the paper gives a brief introduction to RL, and then it gives the background of how policy gradient methods work in the second section, notation and background. And on the third section, it describes its own methodology for the evolved policy gradients method. It posits its own objective functions to the optimization on. And then it explains the architecture of the loss function, the novel concept that's introduced by this paper. And then it presents some experiments on some physical simulations, like ants walking to reach a target, some AI agents. Okay, so let's get back to the beginning. Somebody's saying something in the chat. Oh, okay, Michael is leaving. All right. Okay, so the introduction. So the paper presents the concept of evolved policy gradients with this life example in the first paragraph. So when a human learns, it says, to solve a new control task, such as playing the violin, they immediately have a feel for what to try. At first, they may try a quick, rough stroke and produce a screech will, they will intuitively know this was the wrong thing to do. So basically, humans, when they're trying to learn a new task, like playing the violin, they already have some kind of prior knowledge before they pick the violin. They have been exposed to, classical music, or maybe they have learned some similar task, like maybe playing the piano. So they have some knowledge of good sounds versus bad sounds, or harmony and cacophony. So they immediately, when they try something, exploring the new environment, which is the violin, they try something to see how it sounds. And if it sounds bad, then they don't try it again. So that's the reward. If it doesn't sound, it gets a negative reward, the human that is, and doesn't try the same thing again. It explores the environment by randomly trying new actions. So reinforcement learning, and particularly this paper, Evolved Policy Gradients paper, tries to emulate this process. Regular standard reinforcement learning method, it says approach each new task afresh. Initially, they have no notion of what actions to try out, nor which outcomes are desirable. So actually, standard RL methods take a long time to train. So humans, compared to human agents, an AI RL agent takes far longer than humans to learn simple skills, because they learn the most basic things. They start, an RL agent starts being trained on the most basic tasks. So evolved policy gradients try to overcome this by this additional loss function concept. Our aim in this paper is to devise agents that have a prior notion of what constitutes making progress on a novel task. So this behavior is encoded implicitly through a learned loss function, a differentiable and evolved loss function. The end goal is agents that can use this loss function to learn quickly on a novel task. So fair enough. Let's see. So the bird's eye view of the algorithm is illustrated here. So there is an inner loop and an outer loop. The inner loop is the standard policy gradient method, where the policy function is simulated by a neural network, and the outcome of the neural network is the actions. So it's kind of like imagine, if you're familiar with regular deep convolutional neural networks, like an image net data set object classification, you have convolutional layers that outputs 1,000 classes, right? In the RL case, we have a similar feed-forward network that takes the state as an input, like the regular convolutional neural network takes pixel values as an input, right? Each pixel is a orthogonal feature. It's an independent feature from the next pixel. It's an input feature. So in the policy network, in the RL case, let's say our task is to learn how to play an Atari game. So we have only 4 actions for each state, and the input will be the pixels of the game. So there's maybe an adversary trying to attack you, and you're like shooting something to kill the attackers. So the pixel values of each state, of each snapshot, is an input to the policy network, to the deep neural network in the RL problem. And the output is one of the 4 actions. So this is how to think of an RL problem. So yeah, the evolved policy gradients method on top of that introduces a loss function in the outer loop. So it initializes the loss function, and the loss function trains a policy network for only one iteration. And the policy network is trained with NSGD, just like a convolutional neural network is trained. And it trains for one episode, and then the loss function, and then it collects the rewards, the returns, and it goes back to the objective. And this objective is used to update the parameters on the outer loss function. And then when you have a new loss function, that helps train the next level of the policy network. And then this is done in a loop, in a cycle. So the new addition to the regular policy gradient method is to train this loss function. And this loss function, I'm going to come to it in a second, is trained with evolution strategies, not with a regular backpropagation or gradient descent, because it's a transcendental function. It's not explicitly defined. You can't really compute the gradients of the loss function analytically. You can only evaluate its value, so you can only do a forward pass. And so backpropagation is not an option. And we employ, the authors employ evolutionary strategies to train the loss function as a black box optimizer. You don't know what's going on inside the function. You can only evaluate it. So it's just an input-output. And this evolved loss function can be viewed as a surrogate loss. So let's move on to maybe the next section. Okay. So the contributions of this paper is these several bullet points. By the way, this word meta-learning is an important phrase. So meta-learning is a new thing in the RL research world. So it's basically learning how to learn, right? It's meta-learning. They were working on another algorithm called Reptile. I think it's still actually under research. And there's several meta-learning algorithms that OpenAI has been working on. And actually, according to their blog and according to this paper, none of these meta-learning algorithms really do the job well. It's still a work in progress, and neither does evolved policy gradients outperform a regular policy gradient method in regular tasks. It is only superior to a regular policy gradient method in carrying prior knowledge to a new task. So we're going to come back to this towards the end of the paper. So this is the main contribution of the evolved policy gradient method. So the basic concept is this meta-learning approach learns a differentiable loss function for the AI agent, reinforcement learning agent, optimizing the parameters of the loss function via evolution strategies, overcomes the challenges that final returns are not explicit functions of loss parameters. So yeah, I'm just reiterating myself. The loss function is learned through evolution strategies because it's just a black box function. It's differentiable, but you can't really calculate the derivatives explicitly. And also the loss function has a particular architecture that takes into account the agent's history via temporal convolution. So it's this kind of like an RNN kind of thing happening, temporal convolutions. Okay, we'll come back to this in the next section. We have to go over how a reinforcement learning problem is formulated. Because it's like a Markov decision process, a string of states and actions and rewards. And so it's a sequence, a time sequence. And the loss function takes into account the sequence of actions and does some kind of convolution over this temporal sequence. So evolved pulse gradients produces a learned loss function that can train agents faster than off-the-shelf pulse gradient methods. This is one of the promises of the paper. And the major strong point of the EPG method is that it can generalize to new tasks, the kind of tasks that the RL agent was not trained on. So it's like knowing how to play the piano, and that knowledge being transferred to learning how to play the violin. That's the idea. So the reinforcement learning primer is in this section, the background. So the reinforcement learning model is usually thought of as a Markov decision process, which is made of these parameters. S is a state, which describes the environment at a given moment, and A is the space of actions. So we have the state space, we have the action space, and T is the transition dynamic, which is the transition distribution. So it's S cross A cross S, which means you have a current state, and the action and the agent takes an action on that current state with intention to change the state of the environment, but that is a stochastic process as well. Not every time you maybe steer the car to the right, it goes the way the car steers to the right the way you expect, because there might be some stochasticity involved in the environment, like maybe it could skid or something. So that constitutes a little an additional level of randomness, which is encoded in the transition dynamic, transition probability distribution. So we have state, we have actions we could take, and we have the transition dynamic, which is the distribution of the state at the end of the action that the agent takes. And we have the reward process. So the environment gives you a reward for each time you take an action. So this is basically the four basic parameters that make up the Markov decision process. And we also have an initial state encoded by P0. It's the distribution of the initial state S0. It's the probability distribution of the initial state of the environment. And then agent's policy is denoted by pi. So pi is a function that takes in the state and outputs an action. For a particular state, it outputs actually a probability distribution over all possible actions. And you can do a local beam search, or you can take the most likely or the highest probability action to evolve, like to do some rollouts. So an episode tau is described as, with horizon h, is a sequence of states, actions, and rewards. So for the initial state S0, if the agent makes a move, goes to the right, and the environment outputs a reward. If that move got you closer to your goal, then you will have a positive reward for that step. And then it goes like a sequence of events like that. So this sequence is called an episode until you reach to the end of the game. It could be a chess game, a Go game, or an Atari game. So it's a sequence of states, actions, and rewards, and at each discrete time step, t. And there's a discounted episodic return at the end of the game, when you get to the end of the game. So it's a summation of all the rewards that the environment produces at the end of each time step. And gamma is a, let's see, is there somebody saying something? Okay. Charlotte is leaving us. The optimal, so okay, where were we? The reward tau. So at the end of the game, you have a summation of all the rewards, but the rewards are discounted. If it's like a past reward is discounted more than a recent reward, because you're trying to motivate the agent to gain rewards quickly. So the optimal policy is what you're looking for. This is what you're trying to solve for. Pi star for the solution. It maximizes the expected episodic return. So it maximizes the chances of you winning the game, in other words. This is the kind of notation you see in like deep learning study. So this is the expected value with respect to tau, the episode, and also with respect to the policy, and the expected value of whatever lies inside this bracket, which is the reward. So expectation of the reward means you're multiplying with pi and integrating it over all possible actions. And there's tau, so you're also integrating over the distribution of tau. So this can be written out as like r tau times d pi times d tau, and integrated. It's a double integral. So let me skip this ahead and let me see. So, okay, the policy network pi, the pi function is, it takes a state as input and the outputs a probability distribution over the action space. And this is in RL problems is modeled with a deep, with a neural network with unknown parameters theta. So you're solving for theta with like SGD as you would do on a regular neural network problem. Also, there's this concept of surrogate loss functions. So instead of solving this equation, optimizing on this expectation, you optimize on this expectation, LPG, which is surrogate loss function. So the minimum of this loss function occurs at the same theta star point of this right hand side. Let's see. So this procedure, it says, let me read this paper, this last paragraph. This procedure remains limited since it relies on a particular form of discounting the returns and taking a fixed gradient step with respect to the policy. So our approach in this paper learns loss rather than using a hand-defined function such as LAC, which is this surrogate function, loss function. Thus, it may be able to discover more effective surrogates for making fast progress toward the ultimate objective. So, okay, this is the basic premise of the EPG method. So this section describes the methodology of the evolved policy gradients method. Let's see, this method learning approach aims to learn a loss function, L phi, which is learned at the outer loop that trains the policy network that's described in the inner loop. And it's hoped that it's going to outperform the usual policy gradient surrogate loss functions 2 and 3. So this loss function L phi consists of temporal convolutions over the agent's recent history. This is, I find it kind of like a interesting concept. Wait a second, my batteries. No, plug this in. Okay. Carry on. Okay, here we are. I'm still live. Okay. Okay. The meta learning objective. So these two functions, this one and this one, it basically defines the two loops, nested loops. We assume, it says, we assume access to distribution P of M over the macro decision process. So given a sampled MDP, the inner loop optimization problem is to minimize the loss with respect to the agent's policy, pi. So, okay, so let's actually go over the algorithm seems a little too complicated to go over like a phone call. So what I understand from this is theta is the parameters of the policy neural network. And it is dependent on the loss function and its parameters phi. So here's phi here, and here's theta here. So that's how they are linked to each other. This is the inner loop. One second. Okay, so let's actually look at the final, the second equation. So this is the inner loop. This part is the inner loop. This part solves for the policy gradient and optimizes it with respect to theta star being the weights of the policy network. So it optimizes the reward episodic reward function. So reward function actually it acts like a cross entropy loss function in a regular convolutional neural network. And outside we have the outer loop, which optimizes the policy with respect to the loss function parameters phi. So at the final state, phi star, the loss function parameters are learned, which will have trained the parameters of the policy network theta star. So it puts the theta star here inside and the phi star outside here. I'm waiting for the truck to pass. So, and the next section describes the details of the algorithm. Um, and the architecture of the loss function. The agent is, let me see. Why is this not coming on? Okay, never mind. So this section number 3, this section describes the loss function, the architecture of the loss function. The agent is parameterized using an MLP policy with observation space S and an action space A. The loss is a memory unit to assist learning in the inner loop. So this reminds me of like in sequence models, like in RNN. They are doing it with temporal convolutions, which is essentially the same thing as an RNN. So this memory unit is a single layer neural network to which an invariable input vector of once is fed. Yeah, so these are like the fine details of the loss function. It would not be very easy for me to communicate the details. Let's actually move on to the experiments and comparison of EPG with the standard regular pulse gradients methods. So at OpenAI, they have developed these physics-based simulation environments where an agent learns how to do a task. It's called a MuJoCo. It stands for multiple joint contact environments. Like this is one of them. It's a fetch environment. So there's a mechanic arm, robotic arm, that's trying to reach a target in the 3D space. So its inputs are the torque. The agent controls the torque it can apply on the joints on the arm. So it has several degrees of freedom. And by manipulating the torque on its joints, it's trying to fetch particular target point in the 3D space in front of him. They have already also, have like an ant, goal ant, trying to reach a target on the ground. And there's some directional hopper and directional half cheetah, some other agents that can move, just try to maintain an upright posture, like a humanoid, trying to negotiate obstacles and just move forward. So it covers the details of how many cores they use and noise vectors they have used, some hyperparameter tuning they have done to do the evolutionary strategies search on the loss function. So the performance is look at it a little bit. So they are comparing the evolved policy gradient method with the PPO method. PPO is a hard engineered reinforcement learning loss function, and it generalized. It's capable of doing different tasks. Like it's used in robotics as well as it's used for controlling like Atari game agents, video game agents. It's kind of like the default reinforcement learning algorithm that's used in OpenAI. So it's a good ground truth to compare a new novel approach against. And let's see, in all of these environments, the PPO agent learns by observing reward signals, whereas at test time, the EPG agent does not observe rewards. Observing rewards is not needed in EPG, since any piece of information the agent encounters forms an input to the EPG's loss function. So this is the exploration versus exploitation dilemma. The environment is random, and the agent is taking some random actions in order to understand how the environment is going to respond with rewards. As long as the agent can identify which task to solve within the distribution, it does not matter whether design identification is done through observations or rewards. Okay. So, okay, the outputs. They observed that in all experiments, the EPG agent learns more quickly and obtain higher returns compared to the PPO agents as expected, since the EPG loss function is able to tailor itself to the environment distribution it is method trained on. So this is one strong point of the new EPG algorithm over the PPO algorithm. This indicates that our method generates an objective that is more effective at training agents within these task distributions than an off-the-shelf policy gradient network on policy gradient method. This is true even though the learned loss does not observe rewards at test time. This demonstrates the potential to use EPG when rewards are only available at training time. For example, if a system were trained in simulation but deployed in the real world, where reward signals are hard to measure. Yeah. Let's see. The correlation between the gradients of our learned loss and the PPO objective is around 0.5. I don't understand what that means, but let's actually see the nth example. Okay, so there's, let's look at these figures. So okay, I remember watching an animation somewhere on OpenAI blog on the walking ant. So this figure 15 is where I'm looking at. So these are there's a comparison between the PPO and the EPG methods. These are the trajectories. So the light trajectory is the first try, and darker trajectories are most recent try. So after the agent has taken certain number of trials, it starts to perform better in the task of trying to reach the green target. The trajectory is sampled from test time training on 2 sampled goal ant environments. The ant learns how to explore various directions before going to the correct target. Lighter colors represent first initial trajectories and darker are the later trajectories. Wait a second, though. That was okay, this one. So this is a good plot and figure that describes the differences in performance between PPO, which is the regular RL methodology, and the new methodology, evolved policy gradients. So it's about generalization, right? So the promise of the evolved policy gradients is that it generalizes to new unseen tasks better than the regular state-of-the-art PPO methods. So here the ant is trained on moving to the right. So this is the whole thing, the environment and the task that the ant is trained on is just this. This is this initial point, and here's a target. You have only one target that's in front of him. And then the ant is trying to move its joints and make his way towards the target, try to reach the target. So as it gets closer to the target, the rewards are higher, right? So the ant is trained on reaching the target to the right of himself, and there's another target, and then it's trained on these three tasks, and then it's being tested on a new task, which is trying to reach a target that's behind him. So the EPG method, here are the returns. The EPG method actually is superior to PPO method or another meta-learning. This is actually RL squared, which is another meta-learning method. So EPG method learns how to generalizes to new tasks, which is moving to the target on the that's behind the ant. And the returns of the EPG, which is the red line, it basically reaches the RL square, the previous state-of-the-art meta-learning method. The generalization, the goal ant experiment, the ant has only been meta-trained to reach target on the positive x-axis. Can it generalize the targets on the negative x-axis? But wait a second, I saw something, maybe it was not from this paper, but from their blog about generalization. Let me actually go to desktop. Oh, okay, it's here. Okay, evolved policy gradients. Okay, here we go. Is this the same figure? It is indeed. Okay, so okay. Okay, so these figures, this one is meta-trained in the right direction. So let's see. So this figure shows EPG performs just as well as an RL squared algorithm in testing a new task that is similar to the kind of task, the family of tasks that the ant was trained on. But this is where the difference is. So the EPG returns, the red line, is much higher than RL squared when you test it on this new target that is from a different family, slightly different task, because it's the target lies on the negative x-axis on the left-hand side of the ant. So RL squared does not learn how to move to the left target at all. It's just a flat line. But EPG learns how to move even though it has not seen during its training a target that lies to the left of itself. So this is the gain of the new method, basically. RL squared lays flat, and EPG can do better. But there's also one catch that let me find. I read this paper, I printed it out, and I didn't have the notes on the PDF file. Let me try to find that paragraph, and then we'll probably end the discussion. It's 8:50. Okay, different policy architecture. Okay, right here. So, okay, compared to the learning curve, figure 6, which we could revisit. I'm gonna highlight this part. Come on. Okay, so compared to the learning curve, with the same train time and test time policy architectures, the transfer performance is inferior. This is talking about the transfer performance of EPG. So the transfer performance of EPG is worse than PPO or RL squared. PPO, the policy gradient method, and RL squared, the meta-learning method. However, we still see that EPG produces a learned loss function that generalizes to policies other than it was trained on, achieving a non-trivial walking behavior. So this is the only gain of the new method. That is, it outperforms the RL square when the agent sees a new task that it was not trained on, thereby showing that the EPG method generalizes better to unseen tasks. However, at a cost. Cost of the transfer performance being inferior. So different policy architectures and auto-distribution task learning. We evaluate generalization of the auto-distribution task learning of the goal-end environment. Okay, this is what I was discussing. We compare the performance of EPG against mammal and RL squared. Since PPO is not meta-trained, there is no difference between both directions. Therefore, the performance of PPO is the same as shown on figure 10. First, we evaluate all meta-learning methods' performance when the test time task is sampled from the training time task distribution. So, yeah, it seems that the EPG, evolved policy gradient, still has many limitations. It's effective to sum up the discussion, my presentation. The evolved policy gradients is effective at a small family of tasks, like walking towards the right, finding a target to the right of the agent, and then testing it on a target that's to the left of the agent. So it generalizes to a small family of tasks. But it's, of course, not tested on a wider variety of tasks, like teaching an agent how to play an Atari game, and then carrying that knowledge over to a whole new Atari game. So that's a two, wildly different tasks. And EPG is still not, or any other RL method is still not capable of that kind of generalization, but humans are. So there's still a lot of progress to be made to reach generalized artificial intelligence in this context. And the drawback of EPG is it gains in generality compared to the state-of-the-art methods, but it loses in performance. So I hope I still have some of you online. Let's see where we are. Stop sharing. Okay, so this is all. If you have any questions or comments, this is the time. Otherwise, it's 8:55 here. It's been almost like an hour. It's a good time to stop. Does anybody have any questions or comments to make? Make some noise, people. Let's see. Okay, then. Thanks for your participation. I'm going to hang up the call here. See you all in about 2 weeks in the next. Yeah, thanks. You're welcome. See you all in a couple weeks in the next AI discussion group. Okay, cheers, everyone.